Good afternoon, everybody. My name is Easwar, and I'm a software engineer on the gRPC team at Google. Welcome once again to gRPC Conf, and thank you all for sticking around for this long. So today I'll be talking about load balancing in gRPC. So if you're like the most interesting man in the world and you run a single server, then load balancing is not for you. You can head early to happy hour, have a few drinks, go back home and chill. But for most of the rest of us, we run multiple server backends and we have multiple clients that are sending multiple requests to these server backends. So load balancing is all about distributing client traffic across our backends in a fair and appropriate manner. So this talk will focus on application level load balancing or L7 load balancing and not network level load balancing, which would be L4 load balancing. So in gRPC, load balancing happens on a per request basis, which is at the application layer, and not on a per connection basis, which would be at the network layer. So by distributing client traffic across our server backends, load balancing attempts to ensure that there are no hotspots in our server fleet, and thereby tries to guarantee that our service is highly available, scalable, and highly performant. Now, at a high level, you have two options for load balancing. One is server side and the other one is client side, and this is a choice that applications need to make upfront. So with server side load balancing, our clients send all traffic to a proxy, and the proxy takes care of distributing this traffic across the server backends. The nice thing with this approach is that the client can be very simple. It just sends all its traffic to the proxy, and you can put all the load balancing logic in the proxy in one place. But this is also the disadvantage of this approach, because all traffic now needs to go through the proxy, and therefore the proxy can very quickly become a performance bottleneck and a scalability bottleneck as well. And running a fleet of proxies and maintaining them would have its own costs and can be prohibitive at times. So with client-side balancing, we have clients directly talking to server backends, and therefore we eliminate the proxy, and this gives us good performance improvement. But this comes with its own disadvantages too. Now the whole load balancing logic is moved into the client. So the client becomes a thick, fat client. And in most cases, we would want to support clients running in multiple languages. So this means implementing the same complex load balancing logic in multiple languages. And with this approach, you would have to trust that the clients do the right thing in terms of balancing their load. But when you use gRPC, you get all this for free, because we take care of implementing the complex load balancing logic in the gRPC client. We implement it in multiple languages, we maintain them, and you can trust gRPC to do the right thing. So the component that performs load balancing in gRPC is known by different names in the different languages, but we'll stick to mostly load balancing policy or LB policy in this talk. So an LB policy consists of two major components: the connection management component and the call management component. The connection management component receives backend addresses from the name resolver and is responsible for creating and managing connections to the backends. The call management component, or what we call the picker in gRPC terminology, is invoked on a per request basis and is responsible for selecting a backend to use for that particular RPC. Now, gRPC supports a plugin architecture for most of its components, and LB policies are also one of them. With the plugin architecture, gRPC defines the interface that LB policies need to implement. They implement that interface and register themselves with gRPC at init time, and at runtime, gRPC selects an LB policy based on what is specified in the service config returned by the name resolver. So we'll get into what service config is a little later on in the talk. So gRPC ships with a bunch of LB policies, and the plugin architecture makes it possible for our users to bring in their own as well. Here is a subset of LB policies supported in gRPC. And before we go and look into what LB policy might make sense for your service, let's actually go over a couple of examples. The first one, pick first, is an LB policy that basically connects to the given addresses in order until it can find a reachable backend. So once it has a reachable backend, it sends all the traffic to that single backend. Now, round robin is quite the opposite in the sense that it connects to all the given backend addresses in parallel and attempts to distribute the RPCs across all reachable backends. Now, it's important that you pick the most appropriate LB policy for your service. There are a bunch of cases where pick first would make a lot of sense, like if your client traffic is going through a reverse proxy, or if your clients require soft affinity. This is the case where you would want all requests from a particular client to go to a particular server backend because that server is caching some client-specific data, let's say like a database cache or something. So in these cases, it makes a lot of sense to use pick first. Also, in the case where you have a lot of clients, but they're sending very little load, pick first with randomized shuffling would work great. In most other cases, though, round robin or weighted round robin would be very appropriate. Now, if you're unsure what LB policy to use, or if you think that gRPC doesn't have an LB policy for your use case, please do come and talk to us. We might be able to help you. Or if you have a great idea for a new LB policy, definitely come talk to us. We'd like to collaborate with you in the design and implementation of the new policy and see if we can help the whole community. Cool. So now that we've sort of covered the high-level overview of load balancing, let's actually get into the gRPC client architecture and see where load balancing fits in. So to begin with, the client application creates a gRPC channel and passes it the target URI of the service that it wants to send RPCs to. So a gRPC channel is a virtual connection from the client to the server. The channel is designed to transparently handle the details of name resolution, connection management, load balancing, etc., so that the application does not have to do it. So the application just creates a channel and can start sending RPCs on it. Now, the gRPC channel starts off in idle mode. Basically, nothing is happening in the channel until either the application explicitly asks the channel to start connecting or it sends an RPC. In either case, the channel comes alive, and the first thing that it does is it creates a name resolver and it gives the target URI to the name resolver. And the name resolver then comes back with addresses and service config. So service config controls the behavior of the gRPC client when it's talking to a gRPC server. So it contains things like RPC timeouts, retry configuration, among other things. But it also contains the name of the LB policy to use for this channel and the configuration to pass to the LB policy. So based on this, the gRPC channel then goes ahead and creates an LB policy and sends it the backend addresses and the LB config that the name resolver gave it. So at this point, the LB policy will go ahead and create subchannels. Now a subchannel is an actual connection to a backend address, and LB policies decide when they want to create subchannels, and they can also monitor the connectivity state of these subchannels. So based on the connectivity state of the subchannels, the LB policy sends an update to the gRPC channel. And this update contains two things. It contains an overall connectivity state for the channel, and it contains a picker to use for RPCs. The gRPC channel always uses the most recent picker returned by the LB policy. So when the client application makes an RPC, the channel asks the picker to select a subchannel for that RPC. And once the picker returns a subchannel, the RPC makes its way out of the client through that subchannel. Now, it's important to notice a few things here. So the name resolver can come back with updated addresses and service config at any point in time. So when that happens, the channel takes care of sending that update to the LB policy. Similarly, subchannels connectivity state can change at any point in time, and that is also communicated to the LB policy. And based on these asynchronous events, the LB policy would create a new picker and send it to the channel. Cool. Before we actually go and look at the LB policy API, let's look at subchannels in a little bit more detail. So as mentioned earlier, a subchannel is a potential or established connection to a particular backend address. And the implementation for a subchannel is provided by the gRPC client. But it's up to the LB policy to decide when it wants to create a subchannel and how it wants to manage the lifecycle of that subchannel. So during its lifetime, a subchannel goes through different connectivity states, and these state transitions are communicated to the LB policy by the gRPC channel. All subchannels start off in idle, and it's only when the LB policy asks it to connect, it moves to connecting. And from connecting, it could move to ready or transient failure based on whether the connection attempt succeeds or fails. And subchannels in ready state have a working connection to a backend server. When that connection fails, these subchannels move back to idle. And at that point, it's up to the LB policy again to start reconnecting on that subchannel. Similarly, subchannels in transient failure, they don't have a working connection to a backend server. So therefore, they cannot be used for RPCs. They spend some time backing off, and once the back off expires, they move back again to idle. At that point, the LB policy can request a connection and it'll move back to connecting. So any request to connect on a subchannel that's not in idle is expected to fail. At the same time, subchannels in any of these states can be closed, at which point it'll move to shutdown. Also, it's important to note that most LB policies would be managing more than one subchannel. So they all need a way to aggregate the connectivity states of these subchannels so that they can return a single connectivity state to the channel. So here is a commonly used algorithm that's followed in many of the LB policies that ship with gRPC. So the algorithm goes as follows. Basically, if there is at least one subchannel in ready, then the overall state of the channel becomes ready. Else, if there is at least one subchannel in connecting, then the overall state goes to connecting. Else, if there is at least one subchannel in idle, then the overall state is idle. If there are no subchannels in ready, connecting, and idle, then the overall state of the channel moves to transient failure. And this overall connectivity state of the channel can be queried by the client application using the gRPC client API. Now, LB policies are free to use other state aggregation algorithms as well, and there are LB policies in gRPC which do that. Cool. So let's finally look at the API. But before we do that, it's important to know that the API is experimental in Java and Go, and it's not yet public in C Core, although we're working towards that. So the API defines a bunch of interfaces. The first one that we look at is the builder interface. So every LB policy needs to implement this builder interface and register it with gRPC at init time. So the builder basically has two methods, build and name. So build creates new instances of the LB policy, while name returns the registered name of the LB policy. So for an LB policy to be selected at runtime, the value returned by this name method needs to match what's specified in the service config. The next interface that we'll see is the balancer interface. So this defines the actual functionality that needs to be implemented by the LB policy. So this has a bunch of methods, but we'll look at a couple of them that are invoked in response to events from the name resolver. The first one is update client con state. This is invoked whenever the name resolver comes back with new addresses or service config. So this basically gives the LB policy an opportunity to close old subchannels, create new ones, and things like that. The second one is called resolver error and is invoked by gRPC when the name resolver reports an error. So one important thing to notice here is that gRPC guarantees that methods on this balancer interface will not be invoked simultaneously. So this greatly simplifies the implementation of LB policies because now they don't have to worry about synchronizing their internal state when responding to events from the name resolver. So the next interface we'll see is the client con interface. So this interface is implemented by the gRPC client and is used by the LB policy to communicate with the gRPC channel. Again, this interface also has a bunch of methods, but we'll look at a couple of them. So the first one is called new subcon. So this is the function that's used by the LB policies to create a new subchannel. And the LB policies pass the address of the backend that they want to create a subchannel to, and they can also pass some options. So one of the options is this state listener callback that basically LB policies register with the channel to get notified whenever the connectivity state of the subchannel changes. The next method on this interface is update state, which is used by the LB policies to report new state to the channel. And this state, as I mentioned previously, contains the overall connectivity state for the channel and a picker to use for RPCs. So last but not the least is the picker interface. So this interface is used for every RPC, and this has a single method called pick. So this method is given some information about the RPC, things like the full method name of the RPC, any header metadata that's attached to the RPC, things like RPC timeout, etc. And the picker is expected to return a result quickly. It must not block because this is in the fast path. So the picker could return a result that can be one of 4 types. The first one, complete, is used by the picker to indicate that, hey, I have a valid subchannel that you can use for this RPC. The second one, queue, is used by the picker when it doesn't have an active subchannel, but it's actually working on getting one. So in this case, the gRPC channel queues the RPC and retries it whenever a new picker is returned by the LB policy. The third one, fail, is used when the picker doesn't have an active subchannel, but it has already exhausted all the backend addresses and it doesn't have a working subchannel. So in this case, the RPC fails, except if it was made with a wait for ready call option, in which case the RPC will be queued and retried when a new picker is generated. Also note that additional attempts might be made by the retry code, which is like separate from this whole discussion. The last one is drop. Drop is very similar to fail, except that even wait for ready RPCs are failed, and there can be no more retry attempts even by the retry code. So that's all I have. Thank you for listening, and I think we have around 2 minutes for questions. So if you guys have any questions, I can try answering.
So do you think that, let's say 2 clients want to connect to the server, right? You have a bunch of servers, but have the possibility that these 2 clients get to connect to the same server, even other servers still idle, because this client do not collaborate, right? Both try to connect to a server, but both these 2 clients get the same server. So this server gets busy, but others, let's think a very long, gRPC maybe around 10 minutes or 1 hour. But use this
So again,
policy.
it depends on your load balancing policy. Like
But-
if you're using pick first, then and if all the clients get the same set of addresses in the same order, then they would all connect to the first server. But let's say if you're using pick first with randomized shuffling, then each client will see a different order of addresses and they end up connecting to different servers. Does that answer your question?
Okay, but you still there are risk condition, right? Okay. So you mean, let's say for this time, have a request. Then for server 1 is idle. Then for the next time, so besides
Maybe we can try talking offline. But yeah, thanks for the question. Any other questions?
Do you mind if I add something?
Yeah, sure.
I just want to comment on what on your slide saying these APIs are experimental. I just want to clarify. Don't experimental in gRPC means something different. Doesn't mean we're going to remove it. We might, but not likely. Basically, in gRPC Java, I spent most of my time. Most of our mature and used APIs are marked experimental, just because underlying transport may break this change. Each experimental method or class in gRPC Java has a link to gRPC Java issue where you can take a look at the history and involve yourself in the discussion about stabilizing this API. gRPC Java team takes recurring meetings where we look at APIs, ask for users to be stabilized, and we will take it into account. Is it the case for GoTo?
We don't have regular meetings, but yeah, again, like the balancer API in Go has been experimental for a lot of years, but we don't like actually make too many breaking changes. And even if we have to, then we are very considerate about our users. So we try to reduce the pain as much as possible if we have to make breaking changes. So we recommend, or we encourage you to come and use it and give us any feedback if you can.
Yeah, just to underline that doesn't mean that implementation is experimental. It means this API signature is experimental. Implementation may be quite stable.
Cool. Thank you so much.